So I'd like to begin by thanking the organizers for this opportunity to present my work, in particular for being so nice and flexible and letting me switch at the last minute to a online talk when I was actually supposed to be in Bangalore all week this week, as the original plan was. But for various reasons, I couldn't do that, and I'm happy to be able to at least give this talk. So the talk is about monomers in dimer models at one level. That, if you wish, is the StatMech perspective on this. The reason I'm talking about it here in this workshop, of course, is that we often tend to draw caricatures of singlet states using valence bonds, which are not so very different from dimers, and monomers then are not so very different from spin-ons. And that's kind of the underlying motivation or theme that is driving me to present this here. But maybe I'm jumping ahead. So let me start by saying the punchline, which will come at the very end, is all the work of Zahid Ansari and Shauvik Kundu, two students at the Tata Institute, whose work I'm happy to present today. But the whole sort of technology that uses all the stuff we did earlier, that was developed in collaboration with other students, with Ritesh Bhola, Shaunak Biswas, and Mursaleen Islam. And so this background has recently been published. That in turn was motivated by previous work with another student, Sambuddha Sanyal, and an old friend, Leszek Motrunek. And the punchline at the end, which these two guys are responsible for, is not yet published, but hopefully will be soon. So let me begin by saying that all this started many years ago in 2016, actually, when we got confused about zero modes in the tight binding model of diluted graphene. And somehow one thing led to another, as it often does in physics. And we are here talking about emergent spin-ons and Curie-Tails in random magnets. So I'd like to acknowledge that none of this would have been possible without the work that was done with Leszek and Sambuddha. So let's begin with some very sort of broad brush statements. The one that you hear very often in condensed matter, of course, is that quench disorder matters. It matters because no crystal is perfect. And it matters because these imperfections are often frozen on the time scale of typical experimental probes. So it's good to think of them as quenched rather than annealed. In transport theory, we know that these kinds of things lead to scattering and diffusion if you are able to think in a particle sort of picture, semi-classically, for example. But if the wave nature is important, then they can localize, which is even more interesting. But that would be on the metals side of this conference. I want to stay on the insulating side of this conference. So I'm not talking about particles scattering or matter waves localizing. But I do need to introduce sort of the paradigm of percolation, which describes perhaps the simplest instance of how random medium influences transport. And we are going to need that in a tangential way when we get to the sort of body of the talk. So let me just start with this. If you have a classical fluid like oil coming out of some deep oil well, and it's coming up through some porous medium, it's really the random geometry of the medium that is determining whether or not you can get the oil up. And people have thought about it, of course, in many different ways for hundreds of years. But sort of a mathematically precise paradigm was introduced maybe 70 years ago about, which is now called percolation theory. This was, of course, the classic work of Broadbent and Hammersley, who said, if you have a porous medium, the important question to ask is, going along the pores of the medium, do you have end-to-end connectivity in the thermodynamic limit? Can you go from one end to the other? And what they observed was that if you look at this in very simple model systems, you just take a regular lattice, like a square lattice maybe, or a cubic lattice, and you randomly dilute it. And then you ask, going along the existing sites or the surviving sites and links of that lattice, can you go from one end to the other? They found that the answer changes abruptly as a function of dilution, which is their surrogate for porosity. And there seems to be something like a sharp phase transition. So this was the observation. And so this is really very nice for us to think about from a physics point of view, because, we spend a lot of time teaching phase transition and critical phenomena to students. And perhaps the simplest example of a critical phenomenon is exactly this one. You take a regular lattice, dilute it with some fraction NVAC, and ask for the probability to go from one end to the other along the surviving sides, right? How does this probability scale as a function of, how does it behave as a function of the dilution, NVAC, and L, the system size? And the answer, as I was saying, is that there's a sharp threshold behavior in the thermodynamic limit. This is a percolation transition, and it's the simplest geometric example of a thermodynamic phase transition. Basically, this probability goes to 1 in the thermodynamic limit if the dilution is below a critical dilution, and it goes to 0 when the dilution is above a critical dilution. So it's a dimensionless quantity that obeys a 0-1 kind of threshold law. And interestingly, the approach to the thermodynamic limit in the vicinity of this threshold is very interesting. This function, which is a function of 2 variables, now collapses, into a single function of a scaling variable of the type we are familiar with in regular phase transitions, where delta is the deviation of the dilution from the critical dilution, and there is some power of L. And the right way to think about this, of course, is to say that there's a correlation length in the system, which is diverging as 1 over delta to the power nu. And this argument of this function is just the ratio of the 2 lengths, the size of the system and the correlation length. So there's a diverging correlation length in this system, which you should think of really as the typical size of a connected region, a connected component of the lattice. And importantly, this function f of x, we expect it to be a universal scaling function. The exponent nu is expected to be universal. Only the critical dilution should depend on microscopic details. Like if you do it on a square lattice or a honeycomb lattice or a kagome lattice in 2 dimensions, the number n critical will change, but nu won't change and this function won't change. That's the idea, right? This is something we are very familiar with from our renormalization group way of thinking about phase transitions. And this is perhaps the simplest geometric example of something like this happening. Of course, if you go to 3 dimensions, on the other hand, f of x and nu will also change because, universality does not extend across dimensions. So there are universality classes labeled by dimension, and these are properties of the universality class, not the lattice itself. This, on the other hand, is a property of the lattice, right? So this is the story for regular percolation. And the really cool thing here, of course, is that if you're sitting at the critical dilution, the probability to go from one end of the sample to the other simply doesn't change with scale. And if you think about it sort of without being aware of sort of this whole background of scaling and critical phenomena, this is an amazing statement. But it's true, right, at large enough scales. And that's quite a remarkable thing. So this was sort of my 2-minute introduction to percolation theory. And I need it because we're going to look at a very unusual example of percolation. So I want everybody to be on the same page about that. Okay. So let's see, what do I want to talk about next? Well, I want to emphasize before I go any further that this is not a very artificial situation I'm talking about. What I want to talk about is vacancy disorder, right? That's what percolation is about. Now, vacancies are a very common thing in magnets because you often have non-magnetic impurities that substitute for the magnetic ion, like, gallium in place of chromium in SCGO, zinc in place of copper in some high TC insulator, and so on, right? So this is something really important and commonplace. And if there's an interesting phenomenon lurking behind this commonplace thing, we'd like to get at it. So we are talking of random dilution of some underlying lattice. And it models either missing atoms in the crystal structure or substitutional impurities, right? And what I want to talk about now is something, far removed from solid state physics at first sight, but as you will see, there's a connection. So I want to talk about the classical statistical mechanics problem of putting dimers down on a graph, on a lattice. What do I mean by this? Well, dimers in StatMech, as I'm sure all of you know, are simply objects that live on links of the lattice and touch the two ends, touch the two vertices joined by that link, with the rule that any vertex should not have more than one dimer touching it. That's a hardcore constraint. And when we talk of the dimer model, we are usually talking of the fully packed dimer model, which is to say we want to put as many dimers as possible down on the lattice, obeying this hardcore constraint. So we want to match each site to an adjacent site monogamously. That's another way of saying it. And this is precisely the problem that graph theorists and combinatorists call the matching. And in that language, what we call the fully packed dimer model is the problem of perfect matchings. If you can't put enough dimers down so that every site is touched by a dimer, we would call that a monomer dimer model. And that's just the problem of maximum matchings, or just matchings, not perfect, right? So as you can all see, I've already introduced this idea that not all lattices are of the type where I can put dimers down in such a way that each site is monogamously matched to an adjacent site, right? And this, of course, you know very well. If I take a lattice with an odd number of sites, naturally, I have no perfect matching. That's a trivial case. But the point is, there are much more non-trivial reasons why sites have to remain unmatched in the maximally packed dimer model or the maximum matchings of that graph. And that is what is relevant to our analysis, it will turn out, of the effect of non-magnetic impurities in frustrated magnets. So that's kind of the background. I'm trying to stitch together some sort of work in StatMech with some consequences in magnetism, right? Let me just say this again carefully. So why should we care? Well, we should care because, you know, one picture we often have for at least magnetically disordered states of frustrated magnets is that you have these spin-half moments and they form singlets with some other spin-half moment. And really the physics is the physics in the singlet sector, at least the physics is the physics of the reorganization of these singlet pairings. And the crudest way to think is that a singlet between two spin-half moments is like a dimer. And actually, this idea finds expression in computational methods as well, right? We use the valence bond basis which kind of makes this more precise. So, for example, there's some very efficient quantum Monte Carlo methods that work in the overcomplete basis of A-B valence bonds on bipartite lattices. So the idea here is that your lattice has a natural bipartition into A and B sites, and A sites only have B neighbors and B sites only have A neighbors. And then you can construct a basis, which is very overcomplete actually, of valence bonds where each A site is matched to some B site, right? If you can have a perfect matching. You can do this with nearest neighbors. Otherwise, you drop the nearest neighbor restriction and you just say you have this overcomplete basis of any A matching any B. Incidentally, it's now been proved that, well, okay, let me not go there. So the point is you have this valence bond basis, and the basic heuristic we have, and this goes back to very old work from the days of high TC, I think, early days of high TC. The basic heuristic is that antiferromagnetically ordered states have valence bond pairings at all scales. So if you make some sort of histogram or probability distribution of the physical length of a valence bond, how far away is the B site that is matched to a given A site by a valence bond or a singlet, that actually decays as a power law, some kind of power law in this basis for an antiferromagnetically ordered state, for example, the square lattice antiferromagnet. But if you have a magnetically disordered state, like a valence bond solid or a spin liquid, one expects that the ground state in this basis looks like it has short range valence bonds. And in that case, you can start modeling it even by nearest neighbor valence bonds, and that's the connection to dimers, right? And this connection between valence bonds and dimers, short range valence bonds and dimers, can be made more precise in some sort of large N limits. For example, bipartite SU and antiferromagnets have this limit where so what you're doing is on one sublattice you put the fundamental representation of SUN, and on the opposite sublattice you put the complex conjugate of the fundamental, and you write down some model Hamiltonians that you can view as generalizations of the SU2 Heisenberg antiferromagnet to SUN. Now, in the large N limit of such models on bipartite lattices, it's not hard to show, and this was first done by Reed and Sachdev, that the ground state in the valence bond basis basically consists of some nearest neighbor pairings into valence bond. So, in other words, you can describe it in terms of a dimer, right? And so this connection between valence bonds and dimers is not all that imprecise either. It's not precise, but it's not all that imprecise either. There are some controlled limits in which it's precise. So that's kind of the point I wanted to make. So going further along those lines, why should we care? Take two. Well, as I said, you have this connection, and this connection was anyway used extensively by Roxar and Kevilson, who developed this overlap expansion that tries to approximate the quantum dynamics in the singlet subspace of antiferromagnets by working with nearest neighbor valence bonds and writing down a dynamics for the nearest neighbor valence bonds. And this is what has come to be known as quantum dimer models. And in effect, what it's doing is, if you think of it from a statmech perspective, it's taking a classical dimer model and endowing it with some quantum dynamics, right? And the idea is that it's a model or an approximation for the singlet subspace dynamics of a spin liquid phase, for example. So this is another reason why it's interesting to think about dimers. And this really brings me to my main point. All of this work, all of these ways of thinking have been designed for the case where if you want to work with dimers alone, if you want to only make nearest neighbor valence bonds, you can always at least find a perfect dimer couple. Fully packed dimer models have lots of states on these lattices, on these pure lattices. And so you can at least generate lots of singlet states. Then it's a different matter whether the dynamics in that subspace is a good approximation to the dynamics of the antiferromagnet. But you can at least start with it. But if the lattice cannot be perfectly matched, then what do you do? So if you extend this Roxar-Kevilson picture, then there's a natural answer. You would say that if the lattice cannot be perfectly matched, then there's going to be some monomers, some unpaired sites, and that's like spin-ons. So if you restrict yourself to nearest neighbor valence bonds, then these spin-ons will be free. But that's of course an approximation. What will actually happen is that longer range valence bonds will quench these spin-ons into singlets. And so then the idea would be, by knowing something about the monomers in a dimer model, you can, just like Roxar and Kevilson model the singlet sector dynamics, you can model the low energy spinful excitations. Sorry for this typo. I think that's an autocorrect that I missed. It should be spin-ons, not spin-offs. But anyway, just like Roxar and Kevilson model the singlet sector dynamics, you should be able to model the low energy spinful excitations by starting with monomers of maximum matching, on a lattice which doesn't admit perfect matchings, and then asking for what would be the minimum length of a valence bond needed to quench a pair of such monomers into singlet states. Notice I'm already mixing up monomers and spin-ons in this heuristic way of thinking, right? And why is that a low energy excitation? Because the intuition is that the longer range valence bonds will have a weaker binding energy and therefore a lower gap to excitations. So that's sort of, these are all the heuristic reasons for caring about monomer dimer models or maximum matchings of diluted lattices, because we expect there will be interesting consequences for magnets, especially frustrated magnets that have short valence bond phases on such lattices. So is the motivation, I really wanted to get this motivation across. So if there are questions, I'm happy to take them now about this motivation part. No? Shall I proceed? Okay. So that's sort of the spiel for saying what I'm doing is not a complete waste of time. Now let me say what we did. So I think I should start with a picture because, as we know, pictures are supposed to be worth 1,000 words. So this may not be worth 1,000, but it's worth a lot, I think, for me at least. So this is how we started thinking about it. We were looking at a completely different problem, and we were talking of diluting the honeycomb lattice. And I'll mention why we were doing this in a different context later. But we were diluting the honeycomb lattice, and we noticed, translated to the language of monomers and dimers, that if you have 6 vacancies, which are these red squares arranged in this triangle pattern on a honeycomb lattice, no matter what happens in the outside world, there's got to be one monomer that has to live here in the dimer model. In other words, you simply cannot find a perfect matching of this lattice because at least in the visible pink region I'm showing, there's got to be one more. So there may be more monomers outside. The rest of the world might be perfectly matched. I don't know all that because that depends on where else there are what other vacancies. But if you just have these 6 vacancies in this pattern, you must have one monomer that lives here in the maximally packed time. So that was the first observation we had. And we found this very interesting because it gave us something interesting in a different context. But I just wanted to show this picture to tell you what I'm talking. Right? And we call such regions that are guaranteed to have monomers inside them. We call them, for whatever reason in this earlier paper, R-type regions. So I'm just going to remain faithful to that terminology. So I'm going to keep talking about R-type regions. And for me, R-type regions are parts of the disordered lattice, the lattice with vacancies or bonds diluted, that is guaranteed to have a certain number of monomers that live inside it in the maximally packed dimer model, no matter what happens in the outside, independent of what happens in the outside. That's the key part. Okay, those are what I'm calling R-type regions. Okay, and right now this seems very ad hoc and mysterious, but if you just stare at this picture and try to imagine making a perfect dimer cover of this whole graph, and you can take some nice boundary conditions, periodic in both directions, even by even, whatever, you'll find no matter what else you do, whether you dilute some other sites or not, you simply can't get away with less than one monomer on this lattice. And that one monomer one of them has to live here. There may be another monomer somewhere else, depends on the boundary conditions. But inside this pink region, there's going to be one. Okay. So, if I'm drawing such pictures, I should back off a little and ask what do people actually know about perfect matchings and criteria for perfect matching. So let me just state the result that's well known since the 50s or 60s. So statement is, if you're asking whether or not there are perfect matchings of a particular graph, you construct an anti-symmetric adjacency matrix, and we like Hermitian matrices. So let's put an I in front of it. So let's construct a pure imaginary anti-symmetric adjacency matrix, right? It doesn't matter what the matrix elements are, but they should be non-zero only on links of the lattice, right? That's why it's an adjacency matrix, right? So you construct such a matrix, and the statement is, if it has no topologically protected null vectors. What do I mean by that? I mean, these matrix elements are just some numbers, right? So if there is a zero mode of this matrix and it goes away if I change the numbers a little bit, that's not a topologically protected null vector. But if the null vector survives, if I perturb the matrix elements a little bit, so I can't make non-zero elements zero and zero elements non-zero, but I can take the non-zero elements and perturb them so that they remain non-zero, but I can perturb them. So if under such a perturbation, a null vector remains a null vector, I call it topologically protected. That's a reasonable definition. So if there are no topologically protected null vectors, then there is a perfect matching. Otherwise, there isn't. It's a if and only if. And this is actually the origin of our interest in this problem. We were looking for topologically protected zero modes in the diluted graphene tight binding. So that's how we came at it from the other side. But then there is this whole graph theory literature that goes in the reverse direction. So this picture is what I want to now talk about, in the sense that this is my prototype, and I want to ask, this is a picture I made by hand by putting 6 vacancies at these 6 places. But if I randomly dilute the lattice, I'm going to have all sorts of patterns. So how do I think about what I'm calling R-type regions in that general case? That's the question, right? So let's go ahead. So, but let me just recap. So a lot of this comes from beautiful work done in a completely different context, in the context of actually molecular orbital theory for unsaturated hydrocarbons. He was basically looking to find magnetic moments in hydrocarbons. So he used molecular orbital theory. He was reduced to the question of finding zero modes of some matrix, and he counted them by making the following claim. The number of monomers in any maximum matching of a bipartite graph gives the number of topologically protected zero modes of the corresponding tight binding. This is that anti-symmetric matrix I was talking about. I just translated that to physics language, right? So now this is the non-zero defect generalization of what I said earlier. Earlier I said if there are no topologically protected zero modes, there's a perfect match. But let's say there are some topologically protected zero modes, then there may have to be monomers. What's the connection between the numbers of monomers and numbers of zero modes? Well, they are equal. That's the statement, right? And this is true both for bipartite and non-bipartite graphs, proved by different people, given different names, but it's the same statement. And this is actually useful. I mean, this is an aside. So in that problem we were looking at earlier, you can use this to count the topologically protected zero modes of a 10 to the 8 by 10 to the 8 matrix, which if you think about it purely as a linear algebra problem is quite amazing, but we are not doing any linear algebra. We are doing combinatorics and we are counting, right? So it's actually a very powerful technique. But that's not what I'm after. I want to know what's a more typical version of this region, right? So this is a picture I drew by hand, but you know, it would take a very rare configuration to produce this, right? You can even estimate the probability that this happens in a box of size 10 by 10, and it's a small problem, right? So what's a more typical example of R-type regions? Do they really exist in bulk or what? That's the question. So that involves asking, what do R-type regions or these zero modes look like, right? Our original interest was in, like I said, in the particle hole symmetric graphene problem, undoped graphene problem. So but you know, the interest today is in their consequences for magnets. So, but either way, what we want is a general way of identifying all possible R-type regions, which would give us, if you wish, in the language of zero modes, a maximally localized basis for zero modes, right? But we basically want to know how to identify these regions. And there's a partial answer from Longuet-Higgins. He thought about this a little. And his statement was, if you take all possible maximum matchings or all maximally packed dimer covers of the lattice, and just if any of them has a monomer at a particular site, you label that site red. So you've looked through all the maximum matchings, all the maximally packed dimer covers, and wherever in any one of them there was a monomer, you mark that site red. Then the set of all red sites is the set of places where a monomer can live, right? So whatever these R-type regions are, if you take their union, if you just sum them up as sets, right, they will give you all these red sites. But we are not interested in that. We want to have some sort of local picture and say, okay, in this region, there's a monomer, right? Or there are 3 monomers that have to live here, no matter what happens elsewhere. Because the intuition is that monomers localized in a little region are like local moments that are formed because of dilution, and they will have a response then. If you apply a magnetic field or if you measure the susceptibility. That's the intuition, right? Going back to this picture I gave you about monomers being spin-offs. So I want to try and understand that. So I would like something more than this global answer. I want a local answer. In this region, how many monomers will I always have, right? And it turns out there's a very nice theory that helps us do this. And this is the punchline of our previous work. We could answer this question. We could look at these R-type regions, and let me tell you how. So this goes under the name of the Dulmage-Mendelssohn decomposition. It's a structure theory of graphs that works with maximum matchings to decompose the graph in a special way. And then by using that decomposition, we could essentially construct a complete set of R-type regions given a graph. So you give me a diluted lattice, you tell me where the vacancies are, and I can go in there with this sort of procedure that comes from this theory of Dulmage and Mendelssohn, and I can draw these boundaries, and I can tell you, here, this is the boundary of one R-type, here's the boundary of another R-type, and these will be non-overlapping regions, and I can tell you how many monomers have to live in each of them in any maximum matching, any maximally packed dimer model that lives on that graph, right? So that's what we could do. How am I doing on time? Hello?
So you have roughly 10 minutes, including questions.
Okay, so I try to finish in 5.
Okay,
right?
Good.
I think that would be reasonable, so that there are some questions. So then let me skip the technical details of how we actually use the Dulmage-Mendelssohn theory to do this, but let me show you instead this picture. So but maybe I should say one thing. Let me just say this much. You see, what I do is I take any maximum matching of the graph. This you can generate. There are algorithms that are sort of hard-coded into various packages. We have written our own. These students, they came up with very efficient versions of it. Shaunak Biswas, Mursali in Islam in particular, where we could find a maximum matching of a very large graph because we want to approach the thermodynamic limit. Now, starting with any one matching, the theory says you build these alternating paths starting from the monomers of that maximum matching. So you go on an empty edge, then a matched edge, empty edge, matched edge. That's an alternating path. And as you go along, you start labeling the sites you reach as even or odd, depending on whether you took an odd number of steps to reach or even. And of course, if you started with the A monomer, you label things EA, OA, EA, OA like that. With the B monomer, it's the opposite. Then the theory tells you that you have this decomposition into E, O, and unreachable, and that this decomposition is independent of the maximum matching you started with. That's what the theory tells you. But what we did is we used that to realize that if you now look at that E, O, and unreachable or free labels of each side, you can decompose the lattice in this very special way. You can make these regions that have boundary, which are all O, right? And inside it, the number of E sites are always bigger than the number of O sites by a certain amount. And that allows you to prove that these many monomers will always live in each of these regions. And by using all the properties of the Dulmage-Mendelssohn decomposition, we could prove that these regions are like bags that hold all the monomers of a maximum match. So this was our central result. And we then, knowing that result, we just went ahead and numerically constructed a single maximum matching, labeled things E, O, and unreachable or free, then constructed these boundaries, and then just looked at the statistics of the random geometry of these R-type regions. Now we have a complete set of R-type regions in a graph, in a diluted lattice. We just look at it, right? So the rest of it was a numerical experiment. So this is what I'm saying. We started with a case where you have diluted the lattice in some random way, but making sure that the number of A sites equals the number of B sites if it's a bipartite lattice. And then you find a maximum matching, then build this alternating path tree, and then use this insight of ours to construct these R-type regions, right? And then just look at it. So again, a picture is worth 1,000 words. And the basic picture is at low dilution, these regions percolate, but not quite. So there's a long story here, which I will cut short. But the point is, in 2 dimensions, they almost percolate. So as you lower the dilution of the lattice, a typical R-type region gets bigger and bigger and bigger. So here I'm showing the 3 biggest R-type regions in a 5,000 by 5,000 honeycomb lattice. And you can see the biggest one more or less seems to just percolate, right? But if you look more carefully, it turns out that even the biggest one typically doesn't cross from one end to the other. So the crossing probability doesn't have a transition at any non-zero dilution that we could measure. So it's one of those unusual cases where there's a kind of an incipient percolation transition, but doesn't quite percolate at any non-zero dilution. So that's the situation in 2 dimensions. Since I had only 5 minutes, I'm not going to show the huge amount of data we have establishing that claim. But trust me, we have looked at it honestly, like any other StatMech problem in percolation theory, and our conclusion is best summarized here. So if you look at the probability to go from one end to the other, there's supposed to be a 0-1 law in the thermodynamic limit. We have gone to sizes as big as 26,000 by 26,000. And the point is, the way these curves shift leftwards as you increase the size without any crossing. Remember, if there was a percolation transition, the curves would cross at one point. That's the scale invariant point. Here, they're just shifting leftwards. So this doesn't fit in with the scenario of a non-zero dilution critical point. Instead, what we find that it scales beautifully if you just use that scaling form, but put the critical dilution to 0. In other words, there's an incipient percolation transition as you approach zero dilution. But there isn't a non-zero dilution percolation transition. This is site disordered honeycomb and square lattices. This universal scaling, but with critical value of dilution equal to 0. Okay. So the statement, the spectacular statement that seems to be true, at least to as low a dilution as we could go, is that no matter how small your dilution is, if you're just doing site dilution, as long as it's non-zero site dilution, in the thermodynamic limit, R-type regions are unpercolated, right? They are large, but they are finite. There's a correlation length that's diverging, which is the typical size of these R-type regions, and it's diverging very fast. Nu is 5. So it's diverging as NVAC to the power minus 5, roughly. But they are finite, right? In 3 dimensions, however, with site dilution, we find a real percolation transition, which I'm showing here. So this is 3-dimensional cubic lattice. And now the curves cross. This is the probability to go from one end to the other inside a single R-type region. So now the R-type regions percolate at the non-zero dilution. And I should emphasize these dilutions are all small compared to the dilution needed to break up the whole lattice. So this is deep in the percolated phase of the geometric system itself, of the lattice. So the lattice is not having a percolation transition. The R-type regions are, so the monomers are, because the R-type regions are bags inside which monomers live. So that's the basic conclusion from this study. Now, why am I interested in it? Let me move on. So the point is, our claims now are that infinitesimal dilution seems to localize monomers of a maximally packed dimer model with site dilution in 2 dimensions. Bipartite, this is. In 3 dimensions, there's actually a percolation transition. There's also some other effect that I won't talk about. And one immediate consequence of this is whenever you can show that R-type regions are unpercolated, you can show, and I won't do this, but it's a simple consequence to derive, that if you just look at the standard quantum dimer model, and you can even put plaquette interactions if you like, then an arbitrary state in the middle of the spectrum will have area law entanglement, not volume law entanglement, whenever the R-type regions are percolated. Roughly speaking, because each R-type region kind of behaves independently of area. That's why you get area. So if they are not percolated, you get area. But now I go back to this, all these heuristics I was giving. Do these R-type regions, which have monomers in them, really have...
Excuse me. I think we slowly need to come to an end if you want some questions.
Yeah, so here we go.
Yeah, thank you.
So the statement is, if you take the simplest R-type region on a honeycomb lattice, this is the punchline I was leading up to. So here I've just removed 4 sides. And this is, I'm claiming, the simplest R-type region on a honeycomb lattice. There's one monomer that has to live on these 2 red sides. And then I make another one just to balance the number of A sites with B sites on the opposite sublattice far away, antipodal, right? And I simply look at the ferromagnetic susceptibility in a short valence bond VBS state on the honeycomb lattice. In a, using a designer Hamiltonian to go to a VBS phase, I ask myself, what's the impurity susceptibility of this? And the answer is a Curie tail. So here's the impurity susceptibility. It's linear in inverse temperature, right? And this is exactly the claim we were making. Each R-type region in this case had a spin-on, and these are free spin-half objects, and they're just giving you a Curie tail. So this is the punchline. But you have to be careful. A single vacancy, 2 single vacancies far away don't do this. So this is really a special property of having monomers trapped inside regions. That's my central claim. So let me stop here. Thank you.
Okay. Yep. Thanks a lot for this nice talk.
Thank you. Sorry for going over time.
So we have 2 minutes for questions. So are there questions from the audience? Or any online questions? So yes, one question.
Hi Kedar, this is Yogesh.
Hi.
Can any of this be used for the copper iridate where the coppers are replaced by copper 2+ at some random sites, etc.?
Wait, coppers are replaced by copper 2+, but copper 2+ is a spin, right?
Yes, so that's what I'm saying. So in the honeycomb lattice where
Yes.
you had iridium sitting at the honeycomb with spin halves, so some of them
Right.
become
Oh, so you're saying you
5+.
can have extra. I see. So you're saying you can have extra spins.
Right.
Instead of removing spins, you put spins.
You do both, right? So if the copper becomes 2+, then the iridium becomes 5+, and so the iridium loses the spin, but the copper gains a spin.
Okay. Okay. Yes. So anytime you have this kind of disorder, the point is you have to be a spin liquid or a valence bond solid phase, because that's when this picture in terms of short valence bonds works best. Okay. And that's when I can crudely think in terms of dimer models and their monomers, and then expect those heuristic arguments to work. They work because if you write the wave function down in the valence bond basis, the system anyway wants very short valence bonds.
Right.
This will not work in an antiferromagnetic phase where the valence bonds are power law distributed in terms of their lengths.
Right. No, but I'm assuming that we start from a spin liquid, and
yes.
then the dilution is
yes.
Can your theory, for example, give us what fraction of coppers need to change for us to kill the spin liquid?
Yeah, so for example, what it can do is it can identify motifs like this. It can identify on any particular lattice what's the simplest multi-vacancy configuration that will seed a monomer and therefore a spin-off.
Right. Okay.
So that the idea is that these are correlated effects. They involve multiple vacancies coming together in a certain cluster.
Yeah. Okay. Thank you.
And we can identify those clusters.
Yeah. Thanks. We'll chat later. Yeah. Thanks.
Yeah.
Okay. Any other questions? So then I think in the interest of time, we should stop here, but thank the speaker again. And
thank you.
And we will resume a few minutes later because of the time delay, and we will restart here at 11:35. Thank you.